Hello everyone, welcome to this webinar. My name is Helle Nielsen. I'm Event and Marketing Coordinator at Interacoustics, and I will be the moderator of this webinar. The subject of today's webinar is how to use the residual noise and FMP graph when you do your ABR. The instructor of today, or the presenter of today, is Jos Heinen, which is senior manager for international clinical training at Interacoustics. Jos has been working for Interacoustics for about 7 years, and before he came to Denmark and to Interacoustics, he worked as an audiologist at a clinic in the Netherlands. He worked there for 8 years.
Thank you, Helle, for that introduction. Welcome everyone on my behalf. I am really glad to see that we are with so many participants. So today we will talk about one of the ABR topics, and that is why I think it's good to quickly repeat the principle of doing ABR measurements, and after that I will introduce the topic of today a little bit more thoroughly. What we see here on the slide is a hat. Inside the hat we do have our cochleas, we do have our brain that is registering all the activities, and when we do ABR we place an antenna on the hat in the form of 4 electrodes, 2 behind each mastoid, and then one on the higher forehead, and the last one on the cheek is the ground electrode. Now, if we start recording with such an antenna, what we will see is that there is a whole lot of activity inside the brain. And all this activity doesn't really interest us, but it's there and we're picking it up. And it is actually, there is so much activity that for simplicity I just show that as the darker gray color inside the brain. Now, what we do in ABR is that we put a speaker in front of the ear. We start presenting a sound, and each time that sound reaches the cochlea there is activity moving up the neurological pathway. And because we average over time, the activity from hearing becomes visible. The noise is being averaged away, and in the end it means that you can see this activity which appears on your computer screen as a curve. And the big question of today is, what is in this curve? Is this noise that we just measured, or is this actually a response that comes from hearing? And that is basically the topic of today, and residual noise and FMP quality numbers are the answers to find out if there is a response in this curve. Today's learning objectives are, we will talk about what is residual noise and what is the FMP quality number. Then I will show you where in the software can you find this information, and how do you look at these different parts of information. And then maybe the most important thing is, how do you use this information when making decisions during your measurement. And what I hope that you will get out of this presentation is that if you learn how to use residual noise and FMP information, then your measurements will go much more quickly, because you make the decisions on the right time without wasting time. Also, you will be more confident about the measurements because you will be more certain about the outcome. Let's start with a quiz. I have 2 questions for you. How many sweeps must I collect before stopping the measurement? I will make sure that you can see. It's already you can already see what other people answer to the question. It's very interesting. Many people say other. Strange. Some people say 2,000 clicks. Yesterday we had people saying 1,000 and 4,000. Click on the answer that you think is the most correct. Okay. We see a majority say other. One says 1,500. One says 2,000. I have a second question, but before I go there, let me just say, when I learned ABR in the beginning of the year 2000, 2001, I was taught to always measure 2,000 samples. So I would have expected many people clicking on the 2000 answer. Today that answer is not necessarily the correct answer, but I'll get back to that later. Let's switch to the second question. Why must I repeat each measurement when I do ABR? Maybe the answer is very often the patient gets calmer over time and the second recording is usually of better quality. Or perhaps you think that it is done in order to confirm if the patient produces stable latencies. Perhaps it is to get a better feeling for the amount of variation in the measurements. Maybe you don't have any idea, but in many clinics it's a rule, so you repeat the measurement just because you're told to do so. And then maybe you have another idea. Now we are 10, so okay, so it's a little bit spread. I see that the majority says it's to get a feeling for the amount of variation in the measurements. I like that answer very much. Let's continue with the presentation and see what I have to say about this later. So now we go to the next topic, which is introducing what is residual noise. Now, we just saw one sound being presented, and from that we have the very first curve in our computer. As soon as we present the sound for the second time, there's activity again, and we get a second recording inside our measurement. Now, what is shown on screen now is the average of the two measurements. But the measurements were not the same, so there is variability, and residual noise is defined as the variance of the measurements, the mathematical variance. So if we now add on a third measurement and a fourth measurement, what we will see over time is that the mathematical variance is going to reduce. The longer you measure, the smaller the variance. And if you think about noise, noise is really truly random. It means that it doesn't matter which point on the curve you use for this analysis. You could take 1 point. If you use 1 point for this analysis, the noise value might fluctuate a little bit up and down, but over time it will generally move down. Now, if you use 5 points, like we do here, we use 5 points on the curve, and then we get 5 times a residual noise number. They should be the same number, but we show the average of those 5 points just to make the measurement more stable. What do I want you to remember out the residual noise? First thing, residual noise reduces if you take longer time to measure. Now, in the old days, this was not necessarily true. If the patient would become restless and starts moving, the patient introduces more noise to the measurement and the noise could increase again. But there is another technology which is called Bayesian weighting, which I'm not going to explain now. But due to such technology, the residual noise only goes down. It means that if the noise is relatively high, you can just decide to spend longer time until the noise is low enough. And what do we then call low noise? Well, if you heard us talking about this topic some years ago, we would say 40 nanovolts is low noise. Now, we have learned more about it over time, and in fact, specifically for the Eclipse, we today say 40 nanovolts for adults is low noise if you are doing a neurological assessment. However, if you're doing a threshold measurement, then getting to 40 nanovolts is not really necessary, and you could also say 50 nanovolts is already a low value. We also learned that in babies you get to much lower residual noise values because there is less activity picked up from the brain activity, and that's why 25 nanovolt is considered a low number for babies for all kinds of tests. Let's explain what is the FMP quality number. We look at a curve on the screen, and then we start thinking about, is the quality of this curve good, or is it perhaps bad? I wonder what people say if you ask them, what is high quality? The kind of answers that I expect from people is that some people might say, oh, high quality if the noise is very low. Other people might say, no, high quality depends on the amplitude of the signal. Maybe peak 5 specifically, or maybe several peaks, and the truth is a little bit of both. We look at the signal to noise ratio. So high quality a high FMP number relates to the signal to noise ratio being big. And the mathematics are that the FMP is related to the square of the signal to noise ratio. That's not important to remember. It's important that you know that the higher the number, the better. Here we have the curve on the screen, and just for the diehards amongst us, I will explain how this FMP is calculated. We already know it relates to the signal to noise ratio. The noise is the residual noise, so that is the mathematical variance as I talked about previously. But what is then the signal? If we talk about FMP, the signal is analyzed over a wide range in time. So we don't look at a single peak, we do not even mind where the peaks are, we just take 10 milliseconds, and in that 10 millisecond time window we look at all the signal that is present. And what we need for that is we need the baseline, which is the average of the curve, and then we look at each point in the curve. How far is it away for the average? So here you see a surface that is indicating kind of the signal. If you follow the true mathematics, then the points that are further away from the baseline have a heavier weight on the signal than the points that are very nearby. But okay, signal relates very much to the distance away from the baseline, and well, the signal is then compared to the noise, and in that way we get the FMP number. There is people that always, the question I get a lot is, what does FMP mean? It's a label that people find difficult to remember, and that's why they of course want to know what it means. My opinion is that FMP is a very unfortunate name for a quality number. The F comes from a mathematical function which is called the F function, and that is that those mathematics are used to calculate the signal. And the MP stands for multipoint, and that's because the residual noise comes from a multipoint calculation. Good. What would I like you to remember from FMP? First of all, if the quality goes up, then the signal to noise ratio becomes better, and that's mostly because the noise goes down over time, and that results in a higher FMP. So remember, better quality, higher FMP number. Then a second thing, the FMP relates directly to the chance of having a reproducible response in your measurement. So perhaps it is easier to talk about a confidence level. How confident are you that there is a response, and you can use a percentage number to how to say, to specify your confidence. And for example, being 99% confident that there is a true response is a very high, nice number, and 99% correlates to around 3.1 in the FMP number. Good. So, what do we look for in the software? I'm going to show you a small video. Sorry for that, I was muted for a second because when the video starts, that is what happens automatically. I was just mentioning that we jumped in the middle of a measurement where there was already 3 curves measured, where the peaks 5, they were easily recognized, and now we are measuring at a very low intensity where it is more difficult to find peak 5. And the point here is that we are going to look at the FMP and the residual noise graph, which is highlighted at the top. So it was on the background there. I made it a little bit bigger. What we see happening is that while time passes, the lines become longer, because this is showing how many sweeps are already recorded for the current ongoing measurement. And we see the blue line, which corresponds to a FMP value, and we see the black line, which corresponds to the residual noise value. As I mentioned before, the residual noise typically starts a little bit higher and then goes down over time. And in this particular example, there is a measurement performed until the residual noise reaches a very low level, and the residual noise low levels are indicated on the right hand side. In this little bar graph there is also the current level of the residual noise, and we see it will stop when we reach 40 nanovolts. Now, we have already recorded around 4,700 clicks sweeps, and the user already clicked on this arrow a few times to measure more and more samples because the residual noise was not going down quick enough. And now again he's clicking, so it would go to a maximum of 8,000 clicks. Now, what we hope for is that while the noise is reduced to a low number, that at the same time the quality on this side goes up. So here we have the bar graph showing the FMP number, or the response confidence level, and it also indicates with the arrow the 99% line, which is then considered a reasonable quality, and we're just not getting there. We can now see that the residual noise almost reaches 40, so I think that I will pause the measurement just when that happens. Okay, we see that the measurement has now stopped because we reached a low residual noise, and it is indicated, you can see here that it's indicated in green with the check mark that the residual noise is now considered to be very low as per the protocol settings, and that is why the test stopped. If we look at the curve itself and we look at the previous wave 5, then we might be seeing some bump here. Now, the idea is now that if you had no information about the noise, then you would not be certain if this is just noise or if this is a true response. It is thanks to knowing that the residual noise is low and that the quality was actually creeping up to a almost confident level that I dare to say that here at this very low level there is still a response measured. And that is the power of knowing residual noise and having your quality number. Let's dig into this a little bit further. I am going to put the video back at the start, and just the reason that I show this one is because now we see at the top here, we see the FMP and the residual noise for the previous measurement, which was at 20 dB, which is also of course a low level. But look at how quickly the FMP went up. This patient was very easily measured, and the response was so big that the confidence level went up very, very quickly. We also clearly see peak 5 here in the screen, and the question is, why did the clinician decide to measure all the way up to, well, they waited until the residual noise was low enough. It was 12,000, more than 12,000 repetitions. In my opinion, they should not have done that. I know that this recording was prepared especially for today's webinar, and one of the instructions I gave them is try to be a noisy patient. Otherwise the measurements would go far too quick and I had nothing to talk about. But in this example, I would say even though the patient was maybe still noisy and the noise had not reduced to the bottom, if you are so confident about the peak being there and it's confirmed by the FMP, then you don't need to waste time. You can already continue before you reach the low noise levels. Good. I want to show a few more examples. I'm going to do that from my Eclipse software. What you see here on the screen is a lot of curves, and you see they are not all so nice, and that's also that's the reason why we can learn from it. This was actually measured in a real clinic where they had problems with their installation. We found out that this installation was done right next to the nuclear medicine department, and they were picking up a lot of noise from that department. We also found out that if they moved their equipment away 1 or 2 corridors, then the problem was completely solved. But let's just look at these troublesome results and what the clinician has done to become confident about the measurements. And we start by looking at the left ear, 60 dB. We see 2 curves are measured. Now, why did the clinician measure 2 curves? Well, it is to see the variation over time to see the variation between the two curves. That is the reason, because the two curves are similar in shape. The person became more comfortable about the peaks truly being there, and then peak 5 was labeled. But in fact, this clinician did not use the FMP number, and it did also not use the residual noise. This curve was measured only 1200 sweeps, and the other curve was 1700 sweeps. Now, if we now would add those two together, which I do by right mouse click on the dark blue label and then say create sum curve, then we can see in the FMP result on the top on the left that together the system is confident about this measurement. If we look at the residual noise level, it is still somewhat high. It's not as low as we would like, but 64, it's not really bad. So if the person instead had not stopped the measurement and repeated it, but just make it measure for a longer time until maybe the residual noise level is also low enough, then I think the confidence would have been much higher. And the same I can demonstrate by looking at the 35 dB curves. They are all well, the one I clicked on first has 2800 sweeps, and the other one also more than 2000, and the third one is also more than 2000. So each time more than 2000. If we add them together, then let's see when the residual noise gets low enough. Now the residual noise is almost 41. If I put the last one in it as well, we will see that the residual noise now is really low. So if the person had decided to just measure longer and then measure until the noise is really low enough, then the curve looks much nicer, and I'm sure that the patterns are more easily recognized by adding them together. These measurements will never become very beautiful because they were measured in very poor circumstances, but my point is that they could have used residual noise and FMP to become more comfortable. Okay, so I have a few guidelines and tips about how to use the FMP and residual noise numbers. And let's first talk about how to use these when you do a threshold measurement. Typically, when you do a threshold measurement, you want to spend your time very efficiently. You don't know when the patient becomes wakes up again and so on. So what we do is at the high intensities, we save time by stopping when we are very confident about peaks, particularly peak 5 being present. So you see a nice curve, you get the confirmation from a very high FMP number, and you stop and you don't wait for the 2000 clicks. You can stop as soon as 800 clicks. That's kind of the minimum, which we would say is safe. But stop when you're confident at high levels. When you get closer to threshold, then it is worth spending more time to boost your confidence. And how do you do that? At the lowest levels, you stop when the residual noise is at what we call a low level. So that could be the 50 nanovolts for adults, or it could be the 25 nanovolts for the babies. You might see that when the noise is low, the FMP number is not so high yet. Well, that just means that either there is no response anymore present at the level that you measured, or the response is so small that you can visually see it with your eyes in line with the previous recordings, but it's just not confirmed by the mathematics of the system. So at low levels, stop with low residual noise. Then when doing neurological assessments, you compare right and left. Most important thing is that you compare curves of equal residual noise. If that means that for the left ear you have to measure 1000 and for the right ear you have to measure 4000, it doesn't matter. If the noise is not equal, you are not making a fair comparison. Ideally, you will measure until the residual noise is low for both ears, and because it is at a high intensity, you will see the FMP will be very high as well. So you expect 2 green boxes basically. Then, in my opinion, you do not need to repeat measurements a lot. Of course, when you get, if you do a threshold measurement and you get very close to threshold and it just makes you more comfortable, you could repeat it. But if you have measured until the noise is very low, you don't need to repeat it necessarily. You could also just click on the A and B buffer button. It shows the 2 buffers separately, and that shows also, or visualizes also, the reproducibility of the curves. I think that I have said what I wanted to say. Maybe some of you have picked up some new information, and I would like to go back to our poll question. How many sweeps must I collect before stopping the measurement? Oh, very interesting. We have an additional answer, an additional possibility. I don't want to force you to all select the new answer that became available. You're very welcome to pick one of the other answers, and we can discuss why you think the other answers are correct. As I mentioned before, I learned in the past to measure 2000 clicks. Historically, the number 2000 was picked because people needed a guideline so that they could be relatively certain that the measurement would have a low enough noise, but not measuring so long that it would be wasting time in most of the cases. And then the guideline came that if you measure 2000 sweeps, then in most cases where the patient is cooperating well enough, that is probably good enough. So people started doing that. But basically this guideline could have changed as soon as the residual noise number became available. So today the answer is a fixed number isn't necessary. You need to measure until you have a very convincing waveform, or until the residual noise is low, and that might be much less, and it might be much more than 2000 clicks. Let's go to the second question. You're welcome to click on your preferred answer. There is no wrong answer. Let's see what your opinions are after the presentation. Why must I repeat each measurement? Now, the first answer, which is that very often the patient gets calmer over time, and the second recording is usually of better quality. That is something that many clinicians experience, that you start measuring and then the second recording is much nicer and you become much more confident about it. But that's not the real reason. And it's not really necessary. With modern technology, you can just measure one recording, and if the patient gets more calmer, your measurement will immediately become more beautiful. So then the second answer, which is a little bit part of a trick question, because I wrote, in order to confirm if the patient produces stable latencies. Well, we are quite certain that patients produce stable latencies. Latencies are only varying from the patient if they have a neurological pathology. But I would say the traditional reason for repeating each measurement is to get a feeling for the amount of variation in the measurements, or a feeling for the amount of noise in the measurement. So that is what the traditional reason was. But since noise is now given as a number, and you know what low noise is, you could get this feeling just by reading the number. And then if you know it's low noise, then you know that if there's a bump in the curve, it probably is a response. And if it is high noise, then this bump could be noise, and you don't make a conclusion based on that. So I'm glad to see again that people decided to also select the new possible answer, which is that in fact I measure long enough so that the residual noise becomes very low, and repeating a measurement is often not necessary. Good. I would like to thank you for listening so far. I really hope that I've also given you new thoughts, and for those of you with lots of ABR experience and maybe educated a long time ago like I was, there is now reason to have a little bit of discussion about a few things. In case there is questions, comments, please type them in your chat box, and then Helle will read out the questions and I will answer them as good as I can.
Thank you, Jas. We have a question here. Can PAM impact on the FMP value?
It's a very good question. I like it also very much. And coincidentally, if I move back to my sharing my recording from the software, I'm making sure that you can see the software again, because there was a recording with the PAM on it. So for those who don't know exactly what a PAM is, the PAM is the label for a very high peak in the measurement that appears after peak number 5 and which results from neck tension. These type of neck tensions and these PAM recordings, they can only appear if the patient can hear the presented sound. So having this effect in your measurement is a proof of hearing the sound. And what we can see on the right ear is that there is a very high bump, let's say between 12 and 16 milliseconds. This is a PAM from this patient, and we can also see at the lower levels it was still present. Now, it does have an impact on the FMP because it is very big. It does have a very big impact on the FMP. And remember that the FMP is calculated in a range which is 10 milliseconds long. And for this particular measurement, this range is placed from 5 to 15 milliseconds. That is because the protocol that we used for this measurement is a protocol that is normally used on babies. And on babies, that is the range in which we expect the peak 5 to appear. But at the very high level, we see peak 5 in this measurement is around 7 milliseconds, and the PAM is still clearly within the FMP range. So yes, it does boost the FMP very much, but we do not mind because it is proof of hearing. It is a true response. It just doesn't make the curve more beautiful. Maybe I should also highlight the curves at 30 dB, where, let's move this one down. We had two curves at 30 dB where there was still a little bit of PAM, and you can see actually that now the PAM starts moving outside the FMP calculation range. It's almost moving outside the 50 milliseconds, and that's why the impact of the PAM on the FMP number here is almost not there, where at higher levels the FMP very easily reached high numbers.
There's a question concerning PAM again. Is it possible to get rid of it somehow?
Yes, you can rid of the PAM. The best way to get rid of it is to reposition your patient so that the neck tension disappears. It means removing or placing a pillow under the neck. A technical way of getting the PAM a little bit out is by changing the high pass filter. I think let's try it here. Yeah, if I change the high pass filter, you remove slow movements from the curve, and that reduces the PAM, so it takes less space in the curve, but it also removes part of your useful ABR energy, so that's not the ideal way of getting rid of it. But if the patient cannot get rid of it and you think it's important to get a very clear, nice picture, then you can play with the high pass filter settings.
Can we adjust the range where FMP is measured?
Absolutely. I'm now in the software anyway, so no, I cannot open the settings screen right now. Okay, in the protocol settings, you can change your FMP range. It will always be 10 milliseconds long, but you can make it start at from 2 to 12 if you are testing adults, perhaps, or you move it up from 5 to 15 if you're testing on children. So search for it in the protocol settings, and if you feel the need of changing it away from the default settings, then please do so.
Do we have solid reference for the residual noise values?
I do know that the Eclipse was thoroughly tested by Guy Lightfoot from the UK, and it is in cooperation with him that we came to these recommendations. And I think that generally speaking, the UK has very good they have very good protocols and guidelines. So I can find for you the UK guidelines, and from there you can take the residual noise values also.
Yeah, I have a question more. Based on FMP and residual noise, does the dB/NHL have a clear response?
Okay, you're referring to the measurement that I showed in my video, right? Where I yes, I can bring up that back on the screen. It is now positioned at the end of the video where we can see. Let's make sure that I show my mouse pointer. Okay, so we see at 40 dB there was a clear peak 5, and then at 20 dB there's a clear peak 5, and then at 0 dB there is this bump. Now you asked, do I call this a clear response? Well, if you isolate the 0 dB from the rest, if that's the only curve you have, you cannot label this as being a clear response. It is just because we have the history, the higher intensities, that we can say, yes, I'm confident that this was heard because I see the bump on the place where I expected it. My FMP is like sloping up. It is slowly getting there. It all fits into the nice picture. So I would in fact place a marker for peak 5 on that bump, but I wouldn't use the word clear. I would just say, okay, 0 dB was heard, so in this case the threshold must be somewhat lower than 0 dB. There is a question which is the FMP calculation specific for interacoustics? What do other equipment do? There is other equipment that do use a quality number. Their quality number is labeled as FSP. FSP is almost the same. It relates to a single point calculation. That's why it is a less stable measurement. Besides one competitor having the FSP, I don't believe there is other equipment working with FMP at this moment. Again, if we look at the UK guidelines and the experience they are building up, we know that having the FMP and also having the residual noise is really appreciated by the market, and they kind of advise people to use it if they have it available. So I think we come to an end. So from my side, thank you very much for participating. I hope you enjoyed it. Thank you for today. Hope to see you next time.